there's no defending herself. All right, let's talk about the work that's done on ramps really quickly. Do you think my hand is too yellow? Sorry. Well, you said that the color contrast is funny. Oh. Oh, thank you for. Oh, it's nice with the windows closed. Thank you. All right, work on a ramp.
Yeah, your hand was like white.
Oh yeah. Oh, I'm dressed as a zombie today. Did people see my bite? That's how I got turned. It wasn't Mr. Sampson. Mr. Sampson did not bite me. All right. No. Oh. Yeah. All right, back to the problem. 45 degrees incline for this ramp. 45 degrees. It's not to scale, I'm sorry. 45 degrees. And we're going to put a mass on it. Now this time, you know what? Just because there's getting to be a lot of lines, I think I'm going to use red for the force vectors, just so they stick out a little bit more. We've got our FG. Oh, I didn't give us a mass yet. Let's give us a mass of 10 kilograms again, just for argument's sake, I suppose.
Is there friction on this ramp?
Now let's make it frictionless for now, because really you know that we're just going to be finding normal force and then friction anyways if we do that. And we've been there, done that in the previous unit, so I'm not going to reteach that. But the mass is equal to 10.0 kilograms. Force due to gravity. What was the formula we figured out for force due to gravity parallel? You remember? Let's think about it again. Parallel. Yeah. Okay, so we've got an FG parallel, where FG parallel, or the component of gravity that's parallel to the surface of the ramp, is equal to FG times sine of theta. And we went through, well, not a very complicated analysis to show that this theta value would be the same angle as the angle of incline for the ramp. Okay, we used a few Z patterns and F patterns to get there. So 98.1 newtons times sine of 45 degrees. 69.4 newtons. Beautiful. Now, if we say that this ramp from top to bottom, make yourselves a measurement, delta D, if we say that the ramp has a length, let's make this a little more fun. This is a slide on a playground, okay? This isn't just a ramp. This is a kid's slide.
That means it's
No, it's just a simple old-fashioned one. Slide and Sammy, sitting on the slide, okay? 10 meters, gonna slide down this, actually let's make it less round, 20 meters, 20 meters. 20 meters for Slide and Sammy going down this slide, okay? Yeah, it was an enormous slide on the test. Yeah, 300 meter slide.
900 kilograms.
All right, let's not criticize the exaggerated values on that particular test. All right, so we got this 20 meter slide, and we want to know how much work is, sorry for making you so massive, Tyler. What's that? Oh, did I go the other way with you? Oh, I made you tiny. I made you minuscule. Yeah, but if you want to be a trapeze artist, I'm sorry, you're going to have to slim down. He's already thin and athletic. I'm just joking. How many kilograms did I make you? 40.1 kilograms. Sorry. I hope I didn't offend. All right. How much work is done by gravity? At least I made I had the sense to make the sumo wrestler be a nobody. Joe the sumo wrestler. We don't have any Joes in the class.
Yeah, somewhat.
Are we just assuming that the slide slid the whole distance?
Yeah, we're going to assume that the person goes down the whole slide. How much work is done by gravity on the mass? And we could dress it up and say that it's a person on a slide, but that's not super relevant here. We're just talking about the idea. So we can say that work is equal to force times delta D times cosine of theta. In this case, we're talking about the work done by gravity as it goes down the slide. Okay. So force would be Fg parallel, or 69.4 newtons, times delta D, 20 meters. And the angle between Fg parallel and the displacement down the slide, what is it? It's 0. Yeah, so cosine of 0 ends up just being 1. So somebody with a calculator, 69.4 times 20.
I got approximately 1388.
Yeah, 1388 sounds good. Oh, I'll tell you in just a sec, okay? Because we're talking about the force due to gravity parallel. Really, this is Fg parallel. Goes down the ramp, and your displacement is also down the ramp.
Oh, when you're measuring force relative to the angle of like distance as well?
Yeah, you're really finding the component of force that goes in the same direction as the displacement. And that might get a little bit complicated on a ramp. And so I'm just going to make the recommendation that you find Fg parallel first, that's all. Now you can definitely find the component of Fg that's going in the same direction as the ramp. You'd have to find this interior angle here, and then that would be the theta value for your work formula. But you've got some experience with finding Fg parallel. So let's try not to make up new methods, okay? Not that it's not valid, it's totally valid. In fact, maybe even more conceptually direct. Yeah?
Would we ever have to find the work of something that's sliding down a ramp and then goes on a flat surface, so you have to find a transition of velocity?
Oh yeah, you know what, we haven't gotten to conservation of energy yet, but we may talk about the gravitational potential energy up here and the resulting kinetic energy down here.
And then you continue on.
Yeah, and you continue on, sure. Yeah, you could even talk about the work being done on this thing as it goes down the ramp and say that work is really just change in energy. And so the work done by gravity is what's going to give you that kinetic energy. And if you wanted to, you could say, okay, well, if this was not a frictionless ramp, you could say it's work done by gravity plus work done by friction, and then that would give you your change in energy. And then you can calculate your kinetic energy, 1/2 mv squared, and go on from there. And then we could do a kinematics problem and see how far the kid's going to slide if you know the acceleration on the floor. There's all kinds of stuff we could do, right? But I think that's where we're going to stop today.